Hello, I'm Trevor Plant, and we're going to, in this video, the second of the series, we're going to look at the issue of start and end points when teaching energy. There is always a choice of start and end points, and what we're going to do is have a look at how that choice affects the story in terms of which stores are emptied, which stores are filled, and we'll also look at some of the issues involved. We'll try and do this by looking at examples. The first example we're going to use is of a ball falling towards the ground because of the Earth's gravity. It falls about 1.5 meters, and we play it back in slow motion. You can see that it falls towards the ground, bounces once, comes up, and then it will bounce a few more times, and then, as I think you would all expect, it eventually comes to a halt. The way we often look at the change in the level of energy in the various stores is to use an orange liquid, which is meant to represent how much energy there is in different stores. If I was in school, I'd be using beakers, but I'm at home, so I'm using these glasses. Now, our start point is when the ball is being let go at the top of the drop. So our end point is just before it hits the floor. So the store which is emptied is the gravitational store because it is now much lower in the Earth's field than it was at the start. The store which is filled is the kinetic because it is now moving much faster. But the question is, should we pour all of the liquid into the kinetic store? Well, if you want to be 100% accurate, you would have to say no. On the way down, the ball had to push air out of the way. The air will have got slightly warmer. The ball will have got slightly warmer. So we should pour some into the thermal store. But it's a very small amount. And to be honest, most physicists would ignore that very, very small amount that we have in that store. If we go back to the beginning, though, if we now say, well, we're going to have the same start point, but our end point is when the ball has completely come to rest, we don't need the kinetic store at all because the ball was not moving at the beginning at our start point and it's not moving at the end, our end point. So we just have all of the liquid poured from the gravitational into the thermal. The ball itself and the ground are warmer than they were before. Now, it's difficult to show that they're warmer, but that has always been the case with teaching energy, is to demonstrate that fact. But nonetheless, we know that in principle, the ball and the ground are both warmer than they were. We're going to recap that and have a look at how you might represent this in worksheets, PowerPoints, and things of that nature by looking at this PowerPoint here. So remember, our start point was at the beginning where we just let go of the ball, and our end point is where we had the ball just before it was going to hit the ground. So a store which has nearly emptied, if we want to be 100% accurate, would be the gravitational store, because the ball started off high in the Earth's gravitational field and now it is much, much lower down. The store which is filled is the kinetic store because it's now moving much faster than it was before. So that's the kinetic store. If, however, we choose a different endpoint, if we choose the endpoint of where it's completely stopped its motion, again, it's the gravitational store which has emptied, but it's the thermal store which has filled. So you see, choosing different start and end points tells us a different story. But what about in the real world? What would happen in some examples that we might take from watching YouTube videos? So a mountain climbing example or a pool hoist example, just to show that the subject has relevance outside of what we tend to do in a school laboratory. There are QR codes for these. So if you pause the video, you can check out these YouTube videos very easily. Well, if we talk about mountain climbing, I think it's fairly obvious that most people are going to have a start point which is lower down on the mountain and an end point which is higher up. It doesn't have to be at the peak, but it could well be at the peak. So what would be our energy stores emptying and filling in that case? Well, how come we're able to climb a mountain or walk up a hill or just even walk upstairs is because we digest food. The digestion of food is a chemical process, and so the store which is emptying is a chemical store. The store which is filling, it's the opposite now of the ball falling. The object, in this case us or the mountain climber, is higher up in the Earth's gravitational field. So the store which is filled to some extent is a gravitational store. Now you notice that the amount that I poured out of the chemical store into the gravitational store, it's not all gone into the gravitational store. There's something somewhere else. Well, again, this won't be any great surprise to anybody. Walking uphill or certainly climbing a mountain makes you quite hot. And so the energy gone into the thermal store is what accounts for the difference. Now, again, looking closely at that representation I've done there, you might notice that I've poured about the same amounts into the gravitational and the thermal store. That's not meant to imply at all that the change is 50% efficient, with half of it going to gravitational and half to thermal. Usually the human body works at a lot lower efficiency than that. I'm just making the point that the totals should add up. At this stage, when we're introducing the ideas of energy, we're pouring liquid from one beaker to another. I think it's enough to notice that the amount we've got at the end is equal to the amount that we've got at the beginning in total. And we'll worry about more or less efficient processes later on when the students have done a little bit more. That one's not controversial and doesn't present us with too many challenges, I hope. But the pool hoist is a different thing. So our end point is going to be as the swimmer reaches a safe clearance height after coming out of the pool. So the swimmer has finished his swim and has now been lifted out of the pool. But what are you going to choose as your start point? Well, I'm going to say there are probably two main options you could choose. You start A as the swimmer first gets into the hoist, or start B was as the swimmer climbs into the hoist from the pool. So in the first case, before he's even entered the pool at all, and the hoist will lower him down for a swim, or in the second case, we could choose to start as he's finished his swim and wants to get out of the pool again. So in the first case then, as the swimmer first gets into the hoist, and the end as the swimmer reaches a safe height after coming out. Now, in terms of the energy story, we've got a problem immediately as to which store empties. This is always going to be an issue with anything which is powered from the mains. Which is the store that is depleting? Well, in fact, the contributions to our national grid come from all sorts of sources. So we burn fossil fuels, we have some solar, we have wind, both offshore and onshore, etc., and they all feed into the national grid. So that's a bit of a problem. So what I have found that many teachers I've worked with over the years have thought as a sensible way of introducing things is when you first introduce energy changes and the idea of stores, just use batteries when you've got anything which is powered electrically. So if you've got any electrical circuit or anything electrical device, then you would use batteries. And in that case, then the change is chemical. As they get older and learn a little bit more about the national grid, it would be fine to still put a C there for chemical, because most of our energy still comes from burning fossil fuels in one way or another. So it's not fibbing to say the majority of it comes from a chemical store. If they know more about the national grid, you can say that this is an oversimplification, but still it's probably, if we want to just label it with one letter, it's the most accurate we can be at the moment. What's increased though? Which store has filled? Remember, the swimmer is at this height there now by the side of the pool, and at the end he's going to be back up there. So there has been no change in the gravitational store. The amount of energy in the gravitational store has not changed. So what has changed? Well, the gears and the motor itself and everything else are probably going to be quite a lot warmer. And so what we've actually done is we've warmed things up. It's a thermal store. And this again illustrates an issue when we're looking at energy stories in the real world, is that often if we just look at the energy store which has filled and the energy store which is emptied, it tells us nothing about what the machine is for. It doesn't tell us that what the point of this machine was to safely lower somebody into the water and then get them out again at the end. All it's told us is we made the air and the machinery itself warmer by burning a little bit of fossil fuels. And again, you might say, well, that's not a very useful thing, but it hides the actual use of the device. So energy stores analysis cannot tell you what the object was, what the machine, the device, was being used for. For that reason, it's probably better to go for a start point, which is where the swimmer is lowered down, and so he's still in the water. That's where we're going to analyze as our start position. So again, which store empties is a chemical store, and the store that fills, well, now it's definitely is true to say that he's higher up in the Earth's gravitational field than he was, so we have an increase in the gravitational store. Again, the amount that's gone from the chemical store is not the amount that's gone into the gravitational store, because inevitably the device is going to warm up. So some of it must go into the thermal store as before, as for the mountain climber. But nonetheless, this is a nice example of a real world application of the kind of experiment we might do in a laboratory. We might very well rig up a motor that lifts a weight, an electrical powered motor that lifts a weight from the floor. And we might even take some measurements. And when students are coming towards the end of their pre-16 course, they might do things like calculate the efficiency of the motor. And you can refer them to applications such as this one that mean that it's not just an abstract calculation, it actually has relevance in the real world. So that's really an illustration of how, by choosing different start and end points, you will get different energy stores emptying and different energy stores filling. It'll often be up to you to tell the students what start and what end point to choose, but sometimes they might suggest their own for various reasons. It depends what it is you're trying to teach.
Let's consider the energy story of Tigger being dropped from the upstairs window. Right, so I have Tigger here. When Tigger is held out of the window, it's an upstairs window, it's above the ground. So there is energy being stored in the gravitational store. The gravitational store I will consider to be full for Tigger. When Tigger's dropped, he accelerates towards the ground. As he moves, his kinetic store will be filling. The kinetic store will get fuller as the gravitational store empties. At the point just before Tigger hits the ground, his kinetic store will be at its greatest, so we can describe it as being full, and the gravitational store will be at its lowest, so we can consider it to be empty. The gravitational store is no longer relevant to the situation. All the energy is now in the kinetic store. Of course, when he hits the ground, he comes to a very abrupt stop. In this case, Tigger isn't bouncy.
And just as a recap, if we want to represent the amount of energy, before we start doing any calculations, having a liquid in beakers is a good start, but it's not the only one. You could use a stack of Lego bricks, and then they can stack it one way or stack it another way until they think they've got the right answer. And that leads nicely into bar chart representation of the energy in various stores before and after. So that completes the second of our videos on energy in this series. I hope you found it interesting.